Let's now examine a sample pilot ladder logic diagram that governs the operation of a Y-start delta run reduced voltage starter. This example features an operator-initiated start, followed by an operator-initiated transition from start to run. Rungs 1 and 2 govern both the Y and S contactors. Note the normally closed side of the mechanically interlocked run push button and the normally closed R2 electrical interlock would de-energize the Y contactor coil if either of these opened. We'll discuss this interaction in a moment. Rungs 3 and 4 govern the run contactor only. Note the normally open S2 contact in rung 3. This prevents an operator from placing the motor in run mode without having first placed it in start. Additionally, note the normally closed Y1 electrical interlock. This prevents the R contactor coil from being energized if the Y contactor is already activated. Additionally, note the mechanical interlock between the Y and R contactor. As previously discussed, at no point should the Y and R contactor ever be simultaneously closed. The mechanical and electrical interlocks prevent this most heinous of circumstances from occurring. Note the E-stop, stop, and normally closed overload contacts serve to de-energize all three contactors and de-energize the motor. Let's walk through the ladder logic diagram and see how this Y-start delta run reduced voltage starter works. If an operator were to press start, both the Y and S contactor coils would be energized. When the Y contactor coil is energized, its associated contacts change to their opposite states. The Y1 electrical interlock opens, and the Y primary contacts close. When the S contactor coil is energized, its associated contacts change to their opposite states. The S1 holding contact closes, as does the S2 electrical interlock, and the primary S contacts close. This motor is now in a Y-start configuration. An operator can now release the start push button, and the S1 holding contact maintains this last asserted state. After a predetermined period of acceleration, an operator can press the run button to transition from Y-start to delta run mode. The now open side of the mechanically interlocked run push button de-energizes the Y contactor coil, and its associated contacts return to their deactivated state. The primary Y contacts open, momentarily de-energizing the motor. The Y1 electrical interlock closes. Given the mechanically interlocked run push button is now closed, the closure of the Y1 electrical interlock energizes the R contactor coil, and its associated contacts change to their opposite state. The R2 electrical interlock opens, the R1 holding contact closes, and the R primary contacts close. This motor has been placed in the delta run configuration. An operator can now release the run push button, and the R1 holding contact maintains this last asserted state. If an operator were to press stop, it would de-energize all contactor coils, and all associated contacts would return to their deactivated state. The S primary contacts open, the S1 holding contact opens, and the S2 electrical interlock opens. The primary R contacts open, the R2 electrical interlock closes, and the R1 holding contact opens. An operator can now release the stop push button, and the spring return would return it to its ordinary deactivated state. This Y-start delta run reduced voltage starter is ready to initiate another start-run cycle. The fundamental flaw to our system as currently implemented is that it relies upon the judgment of an operator to initiate the transition from Y-start to delta run mode. Operators, like most of humanity, have a reputation of being fickle mushheads and cannot normally be relied upon to make consistent and sound judgments based off only visual and audible clues. It is for this reason other automated methods are used to initiate the Y-start delta run transition. For example, the mechanically interlocked run push button package could be replaced with a mechanically interlocked rotational speed switch that switches to its opposite states when the motor reaches an acceptable transition speed. Note, since an operator's subjective judgment has been removed, it really wouldn't be necessary to include the S2 electrical interlock. The operator would still initiate a start by pressing and releasing the start push button, However, only when the motor has reached the set speed of the rotational speed switch does the system automatically initiate a transition from start to run mode. The R1 holding contact maintains the delta run configuration if the rotational speed switch is ever reset during a momentary lag in speed. Note the transition from Y start to delta run mode could also be time-based rather than speed or operator-based. We'll discuss reduced voltage starters using timers in later lectures. Here's a graph of line current for a super lightly loaded 6-lead motor started in the delta configuration. The vertical scale is set to 5 amps per division, while the horizontal scale is set to 0.1 seconds per division. Notice the astro-freaking-nomical current draw, peaking out at around 18-ish amps upon being instantaneously and directly connected to full line-to-line voltage. Additionally, note the motor accelerates briskly and reaches a stable current draw in less than 1 1/4 divisions, meaning it took the motor just slightly longer than 1/10 of a second to accelerate the applied load. This obviously wouldn't be the method of choice for a fragile electrical distribution network or applied loads necessitating controlled acceleration. In contrast, consider the graph of line current for the same super lightly loaded 6-lead motor started in the Y configuration. The vertical and horizontal scales are set to the same respective 5 amps per division and 0.1 seconds per division. When each winding is energized by the comparatively smaller line to neutral voltage, notice the motor now takes 4-ish divisions or just under 1/2 a second to accelerate the applied load. Additionally, note that current draw peaks out at only 6 amps. The 6-lead motor started in a Y configuration therefore serves to limit inrush current demand and mechanical stresses to the applied load. Here's both curves superimposed on one another so you can compare the two methods. The delta configuration using line-to-line voltage is yellow. It is characterized by a substantial inrush and a brief acceleration period. The Y configuration using the comparatively smaller line-to-neutral voltage is in blue. It is characterized by substantially less inrush and substantially longer acceleration. Depending on when the transition between the Y start and delta run is made, you'd see a transition from the blue Y start curve to the yellow delta curve. Since Y start delta run reduced voltage starters are characterized by an open transition in which the motor windings are briefly de-energized, you would also expect to observe a momentary transient spike during the open transition. Alright, this about wraps up our introduction to the Y start delta run reduced voltage starter method. In conclusion, this lecture took a brief look at Y start delta run reduced voltage starters. We learned reduced voltage starters are used to reduce inrush current and modify acceleration and starting torque characteristics. Only fully customizable motors with both ends of each winding accessible can make use of the Y start delta run reduced voltage starting method, thereby limiting its applicability to 6 and 12 lead motors and similar devices. When started in the Y configuration, each winding receives only the comparatively smaller line to neutral voltage, and once the motor reaches a predetermined speed, or after a predetermined period of acceleration, the windings are reconfigured in a delta configuration after a brief open transition, and each winding receives a comparatively higher line-to-line voltage. This staged transition serves to limit inrush current and mechanical stresses. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.